Okay, this is our second lesson on optimization, and this is just kind of a representation of some of the harder problems that could occur. But this is kind of wide open. This is not necessarily like classic problems. Just follow along and see if it makes sense, and maybe you can reason through things in the future. So, we're going to start off with this one. A rectangular fence is enclosed, or excuse me, a rectangular field is enclosed by a fence and divided down the middle by another fence. If the middle fence costs $2 per foot and the sides cost $3 per foot, find the dimensions of the largest area that can be enclosed for $660. So when we think about this one, they're giving us a specific cost. We're not trying to find a maximum or minimum cost. We are trying to maximize our area for this amount of money. Let's start by drawing the picture of this fenced-in area. So we have this rectangular field that is enclosed on all four sides by a fence, and it's divided down the middle by another fence. So I'm going to put some variables to these sides. I'm going to say that, again, this is x, this length here, that we use 3 different times. And I'm going to say that the entire side, the long side, is y. So I have a y on each side of this fence. And that's just so I can kind of understand what's going on. Alright, again, keep in mind that we are trying to maximize area. So I'm going to be doing something with the area of this shape and eventually taking the derivative of it and setting it equal to 0. The $660 is what limits us, and so let's think about what the cost of this would be. If I have $660, that needs to equal 2 of my y's and 3 of my x's. But this is just representing length and this is representing money, so I need to change this to represent money. The y's that I said I have 2 of, those cost $3 per foot. And the 2 ends that are x's cost $3 per foot. So I have $3 that is basically this outside perimeter. So 2 x's plus 2 y's. That inside fence, apparently less expensive, costs $2. So $2 times that x. Now this makes sense because this is talking about how much it costs for each of those lengths, just not how much we have. So when you think about writing those problems, make sure you factor the money in. Okay, this kind of works like some of those problems we've done before where we get down to one variable, because over here in our area formula we have 2 variables. So I have this equation that relates them and factors in the money that is needed. And so I can get this down to one variable. So the first thing I'm going to do is distribute the 3. So I get 6x plus 6y plus 2x. And then I'm going to combine like terms so that I have 8x plus 6y. And then I'm going to pick a variable to solve for. I can solve for x or y. I'm going to go ahead and solve for y because we're used to doing that. So if I subtract 8x, 660 minus 8x will equal my 6y. And then if I divide everything by 6, my y will equal 110 minus 4/3 x. So I have this relationship now between x and y. I'm going to take that and plug that in to my area equation for y. So I keep the x, and then for the y I put in the 110 minus 4/3 x. And go ahead and distribute. And now we're ready to take our derivative and find that maximum. So take my derivative, I get 110 minus 8/3 x. I set that equal to 0. I'm going to add the 8/3 to the other side. And then I'm going to divide by 8/3, or flip and multiply, and get that x to be 41.25, and that is how long x is, so that is in feet. Now the question was, if you go back and read the question, it was the largest area that we can enclose. So we need to figure out what that area would be. If our x is 41.25, we know that that's the one side of our rectangle. We need to figure out what the y is so that we can multiply them and get the area. So I find out what the y is by plugging back into the y equation. I'm going to use this one because y is already solved for. So y is going to equal 110 minus 4/3 times 41.25, which is 55 feet. So the short side of the rectangle is 41.25 and the long side is 55. So our max area would be the 41.25 times 55, which is 2,268.75 square feet. And so that would answer our question. I just noticed something. Sorry, reread. Find the dimensions. Dimensions, they weren't asking for area, my bad. They were asking for the dimensions, which would be the 41.25 feet by the 55 feet. But it could have easily asked for area and we calculated it, or I showed you how to calculate it. Okay, for our next example, we are going to find the largest product that we can achieve from two non-negative numbers whose sum is 36. So they've actually given us two things. We are finding a largest product, which means that product is x times y. It's two things multiplied together. And we also know their sum is 36. So whatever those two numbers are, they add up to 36. So right now I'm just using x and y to represent those two numbers. I'm going to scoot this up just a little bit. This one over here, the product one, is the one that we are going to be doing the derivative with because we are trying to find the largest product. And so we're trying to find the maximum product. This is kind of similar to what we just did because we have a relationship over here between x and y, and I have two variables here, and if I get it down to one, it'll be a lot easier. Okay, so I'm going to take this one and I'm going to solve it for y again. So y would equal 36 minus x, and put that into the other equation. And distribute. And then I'm ready to take the derivative because it's a nice polynomial. So when I take the derivative, I get 36 minus 2x. I want to set that equal to 0. Add to the other side. And then divide. So I get x is 18. Well, if the two numbers have to add up to 36 and one of them is 18, the other one also has to be 18. So this one wasn't that bad. These two numbers end up to be the same thing. We didn't have a restriction in our problem that they had to be different numbers. They just had to be not negative. So these are the two numbers that would give us the biggest area possible. It told us to find those numbers, but it also told us to find the largest product. So the product of those two numbers is what happens when we multiply those together, and we get 324. So this was one answer and this was one answer for those questions. Okay, now we're going to get into one that's a little more complicated. We want to find the maximum volume, so I'm going to underline that to remind myself that's what I'm going to be taking the derivative of a right circular cylinder that can be inscribed in a cone of altitude 9 and a base radius of 3. if the axes, so the height and the diameter, coincide. So it looks sort of like this picture. The cone is the outside shape, the cylinder is inside of that cone, and they're lining up nicely. Okay, so what we know is the cone has an altitude of 9, so the distance from the tip of the cone to the base is 9. And it has a radius of 3, so this distance from the center of the cone to the edge is 3. Now, obviously, both of those numbers tell us about the cone, but we don't know anything about the cylinder, just that it fits in there, because it's obviously going to have a smaller radius and a smaller height than that cone. So what we're going to do is we're going to talk about just the cylinder, and I'm going to label its height and its radius as h and r. And then I'm going to think about the difference. So the difference from the top of the cone down to the top of the cylinder, well, if the whole thing is 9 and I'm calling this amount h, I can call that missing distance 9 minus h. And I can do the same thing with the radius. I know the whole thing is 3. If I'm calling this amount r, the amount that's left is 3 minus r. Now, why is that important? It is important because we can look at this as similar triangles or similar figures when we look at a triangle that's just made out of radiuses and heights. So, for example, if I drew the radius up here, this small triangle and this larger triangle are similar figures. So I can make that relationship 9 minus h over r from the small triangle, so that would be the height and the radius of it, would equal the height and the radius of the larger one, which obviously would be 9 and 3. So it's a similar triangle relationship that we've worked with those when we did some related rates problems. Okay, so I have this relationship, and that is kind of like the equation for the money in our example 1 or the sum in our example 2. This is what gives us our relationship between h and r. If you think about the volume formula, we're trying to find the maximum volume of the cylinder. The volume formula for a cylinder would be the area of the base, so pi r squared, times the height, and that would just be h right now. And I'm using this relationship over here to get this down to one variable. So I'm going to solve this relationship over here for h. If I cross multiply, I get 3 times 9 minus h equals 9r. And if I go ahead and divide that by 3, I have 9 minus h equals 3r. And again, I'm trying to get that h by itself, so I'm going to first subtract 9. And then I'm going to divide by a negative. So my h is going to be negative 3r plus 9. Or you could write that as 9 minus 3r. And that is going to allow me to replace the h in my volume formula. So I'm now going to call that h 9 minus 3r. And now we just follow suit like every other optimization problem we've done. We're going to distribute the pi r squared through and get 9 pi r squared minus 3 pi r cubed. Then we'll take the derivative and get 18 pi r minus 9 pi r squared, and we'll set that equal to 0. If I add the 9 pi r squared to the other side, I will get 18 pi r on the right, and I can go ahead and divide by 9 pi and r. So the 9 pi's will cancel and one of the r's will cancel, and I'll get r equals, over here the pi's will cancel, the r's will cancel, and 18 divided by 9 is 2. So I'll get a radius of 2. And if I plug back in, my height would be 9 minus 3 times 2. So my height would be 3 centimeters. And since the question asks for the maximum volume, I just have to figure out, now that I know those two numbers, what the volume would be. So the volume would be pi r squared times height, which would be about 12 pi cubic centimeters. So again, this is probably as nasty as you're going to see from me, but they're all really similar. All the three that we've done here, we had two equations. The one you're trying to maximize is the one that they are asking you to maximize. You take the derivative of it. The other equation is given to you as a way to relate your variables and plug in to get one variable in the other equation. So if you can just realize which is which, you'll take the derivative of the correct one. And that concludes this lesson.